Polynomial functions. So to be a polynomial, and so a couple of things: no negative or non-integer exponents. No negative exponents on the variables, no non-integer exponents. So that rules out square roots and cube roots and all those sort of things. Those are all rational exponents, what they equate to. So none of that stuff. If you're going to be a polynomial, moreover a polynomial function, can't have any division by variables or negative exponents. That's what a negative exponent ends up causing. Or non-integer exponents. So that includes all of the roots, like square roots, cube roots, all of those things. So that would be a polynomial function. Can't have that. And you also have no rational expressions with variables in the denominator. And that's related to the no negative exponents, but it's kind of a bigger thing. For example, this would be a rational expression inside of a function, x squared plus 5x minus 7, and then all of that over x plus 4. Still a function, but it's not a polynomial because you have an expression with an x plus 4 in the denominator. It's a rational expression with some form of a variable in the denominator. So technically this is x plus 4 to the negative 1, but it's being multiplied by here. So it fits this, but we can more generally say rational expressions because this could end up being something like x, a bigger polynomial in the bottom part of that. So no fractions with x's in the denominator at all for that. So to be a polynomial function. Polynomial functions, the generic form of that that you'll see in definitions throughout the world uses this funky notation where we have a sub n and then x to the nth power, and then the next term would have a sub n minus 1 and x to the n minus 1 power, and you would keep going like that until you ended up at a sub 1 x to the first power plus a sub 0. All these a sub n's, those are just coefficients, numbers. Typically, they're integers, but not always. Sometimes they're fractions, but they're just the numbers in front of the variables. And those x to the n's, those are the n and n minus 1 are your powers of x. So if it was the fourth power, you start fourth, third, second, first, x. So in polynomials, descending order is what that's supposed to mimic as you're going through there. That's the generic form of that. We're just going to build off of that. This a sub n that's in front, you may hear me call that the leading coefficient. You may have heard that before. If you haven't, it just means the number in front of the highest power of x. Okay, and that can be handy to know when we start dealing with some of the properties of polynomial functions. All right. Speaking of properties, let's talk about domain, because everything we do within college algebra is going to deal, if it's a function, we're going to deal with the domain of that function. And a domain of a polynomial function is from negative infinity to positive infinity. By laying the rules for a polynomial, to be a polynomial, you can't have x's in the denominator, right? So that's one of our red flags from chapter 3 about domain. You can't even have that to be a polynomial function. And then the other red flag is that you couldn't have, square roots or any kind of roots. Well, with a polynomial, you can't have those anyway. You can't have rational exponents on variables, which is what creates those roots, so square roots or cube roots or anything like that. So there are no red flags if it's a polynomial function. So we know that the domain, if it's a polynomial function, is going to be from negative infinity to positive infinity. Okay. Degree of a polynomial, one of the easier things, but it's also a very descriptive part of a polynomial. Tells us a lot about it. The degree of the polynomial is the highest exponent on x, or if it's another letter in the function, n or whatever, it's the highest exponent on that variable inside of the polynomial. Okay, so first game we'll play is this a polynomial function? If so, state the degree. Okay. Example A. F of x equals 3x to the fourth minus 5x cubed plus 2x squared 6x minus 7. Okay. So really only two things that we need to check here for polynomial function rules. Well, we look at all the variables. Exponents on those are all integers, which is good. And we don't have any x's in the denominator. We don't even have any fractions here to deal with. So this one fits the bill for a polynomial function because it doesn't have any x's in the denominator and it doesn't have any non-integer exponents on the variable. So it's yes, its degree is the highest power on the x's. What's the highest power on the x's here? 4. So this one is of degree 4. And that'll relate when we start solving these things and finding the zeros of that. Knowing what the degree is very important for that. Now this one, f of x is equal to 6x to the fifth minus 5x to the 1/2. Is that a polynomial function? No. Exponents on the variable have to be integers only. I see a 1/2. That's not an integer. Integers are not fractions. So 1/2 being there, that right there tells us, oh, this is not a polynomial. Okay. And the reason is that 1/2 exponent. Anytime we got a rational exponent, something can be written as a fraction as the exponent, then it is not a polynomial. Well, not a polynomial function either. Another 2x to the third parentheses x plus 4 squared. And this is where they can start getting a little bit confusing in that we're still looking at it, but it's not written out in that standard form that we talked about earlier, where you have, like example A is where you got something x to the fourth, then something x cubed and all that stuff. And you could multiply this thing out to get it to that form, but you don't have to in order to just decide if it's a polynomial function or not. Okay, so the first thing that I would look for is, okay, if there are any fraction exponents, they should be showing up here. This is in factored form. So I don't see any. I see a 3 and a 2, and that's definitely not fractions. Those are both integers. If I multiply this out, I'm going to get something with an x squared on it, and then a plain x, and then a plain number. And then I would distribute the cube to that as well. So it's not ever going to turn into a fraction exponent. So it meets that criteria. There's also not any division going on there. It's multiplication going on between those two pieces. So that's definitely fitting the rules for a polynomial function. So yes, it is. And then the degree is where a lot of folks can miss this. You can get it that it's polynomial function, but the degree is a little trickier on this one because it's not in that standard form where you just look to the front and find the highest power of x. Because if I just do that, I would get x cubed, and that's not the degree of this function because it's really x cubed times all of this. Remember, this is x plus 4 times x plus 4. So when I multiply that out, that's going to give me x squared plus some other stuff. But x squared is the biggest part of that. The front is x squared. What's x squared times x to the third? X to the fifth. So the degree for this one would be 5. Okay. Degree would be 5. Okay. Throw some exceptional ones at you here. Cube root of x. And this one, maybe it's an experience kind of thing. If you've seen this in an Algebra 2 course or some other math course, what the cube root is actually the 1/3 power. We start converting from roots to powers. The cube root is the 1/3 power. So there we have a fraction exponent. So it's just like example B where we got a fraction exponent in it. So it's not a polynomial function. Not a polynomial. Period. It won't be a function. Try this one. F of x is 1/5 x to the 8th x squared minus 4 cubed. This one's a doozy. Let's say. We're taking that 1/5 x to the 8th, and then x squared minus 4 is to the third power. So we look for the red flags as far as not being a polynomial. We don't see any fractions as exponents. The 1/5 in the front, it's a fraction, but it's a coefficient. It's not an exponent. So that makes it okay. It's legal to have it there. So I don't see any fractions happening here. So, and definitely no division happening with variables. They're all multiplying together. So this one is a polynomial. The degree, a little trickier on this one. Anybody want to take a stab at it? What does this part in parentheses turn into? The leading term, the first term. X to the, if I cube x squared, would be x to the 6th, right? But it's 2 times 3 is 6. And then 6, x to the 6th times x to the 8th would be x to the 14th. The degree for that one would be 14. If you don't have to multiply it all out, because we're not working toward that, we're just trying to get the degree. So the first term is the only one you really have to work with. So x squared, we cube x squared, that's going to get us x to the 6th. And then if we take x to the 6th times x to the 8th, 8 plus 6 is 14. So we'll get a degree of 14 for this particular polynomial. All right. Let's kind of get into more of a graphical idea, and we're going to make a table is what we're going to do here to kind of help us get our brain going in that direction. So first column is going to be the degree. The second column is going to be the form. And then the name. And then I'm going to sketch the graph over here. It's just a small picture of that graph. All right, so we could have a polynomial function that has no degree. No degree is not the same as a 0 degree, okay? No degree means we've got nothing there. Nothing in mathematics is a zero. So it's f of x equals 0. It's y equals 0 is what that is. So that, as an obvious name, it's called the zero function. Okay. Its graph, you got the coordinate plane, it's just a line that kind of lays right on top of the x-axis is all that is. So the zero function, f of x is equal to 0. It has no degree, and it lays right on top of the x-axis. All right. The next step up would be the 0 degree function, which is f of x is equal to some constant. And the constant when we're talking about polynomials is always this term a sub 0. That's the constant term. It just means this could be any number. So it could be like f of x is equal to 7. But there's no variable on that number that's there. Okay? It's called the constant function. If you think about the graph of that, y equals a number is just going to be a horizontal line at whatever a sub 0, whatever number that is. So I'm looking at something that's positive here. It doesn't necessarily have to be. But it's just a horizontal line that goes across the y-axis at whatever the number it's equal to is. So if it's at 3, you go up to 3 horizontal line, that sort of thing. Okay, so we're building up degrees here. So let's go to degree 1. Degree 1 is f of x equals a sub 1 x plus a sub 0. That's a linear function. In chapter 4, we wrote it mx plus b. That's how we wrote it in chapter 4. It's the same thing. We're just dealing with a polynomial. We're calling it a polynomial of degree 1. Mathematics and mathematicians are world famous for taking something you already know about and telling you it's something different by calling it a different name. So instead of saying mx plus b, we're saying a sub 1 times x plus a sub 0. That's slope and y-intercept, just like it was in chapter 4. It's no different. But because we're talking about polynomials, we can write it in that form, and we know that the graph of that is a line that has some sort of slant to it of some sort. It might be a positive slope, could be a negative slope. Anyway, we know it looks like that. It's a linear function. Out of that, if it's degree 1, polynomials of degree 1 are linear. Okay, and from chapter 4, we also dealt with the quadratic functions. A sub 2 x squared plus a sub 1x plus a sub 0. That's a quadratic. And I don't think I need to keep writing function over and over. It's quadratic. We know that's the same as ax squared plus bx plus c that we dealt with in chapter 4. We're just using a different coefficient way of naming those out of that. But we know what a quadratic looks like. Coordinate plane is that U shape, that parabola, something like that. Quadratic has degree 2. Everything that we already know about quadratics still works, even though we're calling it a polynomial of degree 2. It's still a quadratic, and everything we know about those still works. Okay. Let's get up to degree 3. A sub 3, x to the third, a sub 2, x squared, a sub 1, x to the first. Usually write the exponent, so we'll take it away. Plus a sub 0. That's a cubic polynomial or cubic function. The cubic function, you got the coordinate plane. Depending on what those coefficients are in front of each of those other powers of x, cubic function is always going to look something like this, and depending on what those coefficients are, is how much of a hump in the middle it is. Okay, those coefficients change that about. Okay? And the a sub 0 changes how where it crosses the y-axis. But it generally looks like this. As a cubic function. General shape of that. And then we'll go to degree 4. F of x is equal to a sub 4 x to the 4th plus a sub 3 x cubed 2x squared a sub 1x a sub 0. Technically, it's called a quartic, but most of the time you will hear folks call it a 4th degree polynomial. Okay. And if we continue, we're gonna stop our table here and start repeating stuff over and over after this. But quartic, 4th degree is what you'll hear me say most of the time. I'll say it's a 4th degree polynomial. What's that tell us? If it's a 5th degree polynomial, it means the highest exponent's 5. It goes down from there. So usually, generally, once you pass cubic, you start referring to it as the number of the degree that it is. We don't get too much higher than this in college algebra. You don't deal with larger polynomials than that. Generally, if you're fitting data to polynomials and you're going above degree 4, there's probably something else that could fit better. It's a more advanced equation out of that. So we generally don't get much higher than 4th or 5th degree out of that. But the general look of a 4th degree equation, it kind of mimics a quadratic in that both ends point the same direction. The difference is you can have this hump in the middle here. And if you get a 5th degree polynomial, it looks a lot like a 3rd degree polynomial, just you can have more humps in the middle. 6th degree polynomials can have more humps in the middle, but they look a lot like the 4th degrees. And 4th degrees look a lot like quadratics out of that, okay? There's a table that has a lot of this information in it on page 328 in the textbook if you want to look that up. It's this table. There's nothing, but it's maybe a little better picture drawn for you there. Nothing major. The domain of all of those is still negative infinity to positive infinity. That hasn't changed at all. The range is dependent upon what numbers are in the problem. The range could change from that. If it's cubic or linear, then the range is going to be from negative infinity to positive infinity. Because if you look at the graphs, they're going all the way up and all the way down. Both of those are. The even ones, we're going to go, depending on what numbers are there, we could have a minimum up to positive infinity. If it flipped over, it could go down to negative infinity. But we could get, the range is all dependent on what numbers are in the problem. Okay, so let's just look at some general graphs of some polynomials here. Yeah, example F. We're going to graph, and I'm going to use the graphing calculator to do this. F of x is equal to 1/2 x minus 1 to the 4th power. Okay? So with the graphing calculator, go to y equals, figure out some stuff that I was doing today. And I'm just going to type that in, 1/2 parentheses x minus 1 raised to the 4th power. I'm going to hit graph. And I see what it looks like. Okay? It's a 4th power. This looks a lot like a quadratic, though, doesn't it? Okay? It is a little flatter at the bottom than a quadratic. A quadratic is a little more, has more of a peak at the bottom, or it comes to more of a point. It's not a hard point like an absolute value function would be, but it's a little flat here at the bottom, and which means it doesn't climb as quickly close to the what we would call the vertex of that thing. If you had more terms or x-intercepts involved with this quartic or 4th degree polynomial, you might see some stuff happening in there. So looking at the graph can sometimes be hard to tell what kind of polynomial you're dealing with. We do know, if we just had this graph, we know, oh, it's got to be something with an even degree because both ends go the same direction. That's important to realize it. that we know it's got to be an even degree because both ends go the same direction. Our goal here is just be able to kind of recognize which graph goes with that. So I'm going to take a snapshot of that and put it in our notes. Yikes. All right, so there's a picture of that graph. Let's look at one maybe that's a little more interesting. Let's say we had f of x, which is x minus 1 squared, and x plus 3. What's the degree of that polynomial? What degree would that be? If you were to multiply it all out, what would be the highest exponent? There's a 2 on the first factor. Wouldn't be 4. There's 2 here. What's the exponent on this x? It's 1. So 2 and 1 would be 3. So this is going to be a cubic. So we know it generally has that shape where one end is going down, got a little hump in the middle, and the other end is going up. It could, depending on the coefficients, could change things. So we know that this generally looks like this in some way, shape, or form. It's going to look something like that, not necessarily just like that. Let's find out what it looks like exactly. I'm going to put parentheses x minus 1 squared, and then parentheses x plus 3. Just hit graph. And we see that shape happening. Left side going down, that hump in the middle. Notice where it's touching the x-axis at -3 and +1. Think about how those relate to that original function that we got there in factored form. That's important. We're going to start tying that together as we go forward in the next couple of sections. So, but that's the general shape of that graph. That's what we're looking for out of that. So being able to recognize that. Copy that picture. Put it in my notes. All right, so there's the graph for that. Let's look at describing the transformation. Remember we did this back in chapter 3 and 4 where we shifted a graph up 4 units and left 6 or something like that. So that's what we're looking for here. We're going to transform f of x is equal to x cubed. And here's our transformation. 2 parentheses x plus 1 cubed minus 4. So we want to just describe this. What did this stuff do to the parent graph of x cubed? What does the -4 on the outside do? Down 4 units, okay? So that's usually the easiest one to pick out. Down 4 units. The +1 on the inside. Left how many? 1. Left 1. I'm just trying to be descriptive here. Left 1. And then what's that 2 outside do? Which one is it? Is it a stretch or is it a compression? It's vertical because it's on the outside. So we know it's a vertical something because it's on the outside. If it were horizontal, it would be on the inside of the parentheses with the x. So is it a stretch or is it a compression? And it's all the value of the number out there. It's a big number on the outside, it's a stretch. If it's a small number out here, like 1/3 or half or something like that, that's a compression. It's the opposite on the inside. If it were horizontal, if you had a 1/2 on the inside with the x, then it'd be a horizontal stretch. If you had a big number like 2 on the inside, it'd be a horizontal compression. So this is a vertical stretch out of that. So remind yourself of those rules that we went over there. The rules haven't changed any. you'll get a function to start with, and then they'll give you a transformation that's happening to be able to describe what's going on. Those rules haven't changed. We're just dealing with different functions here instead of x squared or the quadratic or the square root function. We're dealing with polynomials out of that. That's what we're really dealing with. All right, so let's get into the actual solving and fun stuff that happens with polynomials. Okay, so this f of x equals 5 parentheses x minus 2 parentheses x plus 3 squared parentheses 2x minus 3 cubed. Okay. Now, here's some things I want to know. I want to know the degree of this polynomial. Bigger. Think about degree of each term. What's the degree of this first factor here, this x minus 2? It's a degree 1. What's the degree of the second one? It's got a degree 2. So those two together then make degree 3, right? And then what's the degree of this term? It's a 3. Because if I cube 2x, what's 2x to the third power? It's 8x to the third, right? So that's that first term is really the only one you have to work with. And this is x squared, and this is just plain x. If I multiply all three of these together, what's x times x squared times 8x to the third? 8x to the sixth. So this one has a degree of 6. A degree of 6. All right, so that's the first thing we want to be able to pick off from a polynomial given to us is the degree. If it's in standard form, that's super easy. When it's in this form, it's not quite as easy. That's why I try to throw them at you that way. Okay. Now, the next thing I want to do is describe the x-intercepts. And I'm going to put a slash here because there's another name for x-intercepts. Zeros. There's another name for it. Could be called roots. Okay. X-intercepts, zeros, and roots all are synonyms. They mean the same thing. If you're an x-intercept, where are you at on the graph? Yeah, on the x-line, on the x-axis. That's exactly where you're at. So if we were to graph this polynomial, we would see its x-intercepts. Okay? We would see its zeros. We would see its roots. Those are all the same thing. Okay? If we're going to describe those, let's describe what happens. So how do you find the x-intercepts or the zeros of the polynomial? What you do is you take the original polynomial. Mathematically, this is what happens. You take that thing and you set y equal to 0. Well, in this problem, it's f of x, that's the same thing as y. So we're setting the entire polynomial equal to 0. That's what we're doing. And then you solve it. Okay, so to solve this, the first thing you would do would be get rid of the 5 by division there. So we got x minus 2, x plus 3 squared, 2x minus 3 cubed equals 0. Now, back when we did quadratics back in chapter 4, if it was already in this factored form, which this one is, what do you do with each factor in order to find the x-intercepts or the zeros? Set each of them equal to what? Yeah, set each of them equal to 0. Solve them. Solve. Minus 3 plus 3, 2x equals 3 divided by 2. X is 3 over 2. Now, here's where those exponents come back in. Notice that x minus 2, what did that piece have a degree of? 1. So that means 2 is a 0 one time. X plus 3, it had a squared on it. So that means the multiplicity for negative 3 has a multiplicity of 2. What's the multiplicity for the 3 over 2? 3, because the exponent on the outside of the factor is a 3. Okay, multiplicity is based on how many times that factor occurs. This factor, because it's squared, occurs twice. So it's really x minus 2 times x plus 3 times x plus 3. This factor occurs 3 times. 2x minus 3, 2x minus 3, 2x minus 3. So that 0 exists a multiplicity of 2 times for negative 3, a multiplicity of 3 times for 3 over 2. So when we look at that, we find, oh, well, there's this one counts 3 times, this one counts 2 times. That's 5 together. How many times does that one count? Once. That's a total of 6, right? What was the degree of the polynomial? 6. Number of zeros you have matches the degree. Always. Okay? Number of zeros matches the degree. All right, here's what we've got to tie together with these multiplicities. Even multiplicity touches the x-axis. And I always call it bounces off. We'll look at the graph of this in a second. I'll show you what I'm talking about. Odd multiplicity crosses the x-axis. If I graph this polynomial, that's what we're going to do next. So I had 5 parentheses x minus 2, close parentheses, open up another set, x plus 3, close parentheses, squared, another set of parentheses, 2x minus 3, close those parentheses, raise it to the third power. So I typed in that original polynomial that was in factored form. Okay? And I graphed that. You notice what's happening here. Okay. Hard to see it, but I'm going to zoom in here a little bit so you can see a little better. Try to zoom in right in between those two. All right, so we've got crossing the x-axis. This is our value of 3, right? That the other one? No, that's a value of 2. 2 was the positive. That's 2, so it's crossing the x-axis there. That was that 2 had a multiplicity of 1. Right here would be 3 over 2, right? 1.5. It's crossing the x-axis there. That's our odd multiplicities. They're crossing. If I zoom, go back to standard. Where should it also be touching the x-axis? Or should it be touching the x-axis there? Positive 2, that's this one here. It's crossing there. It's crossing at 3 over 2. What's the other 0 of the function? Negative 3. So it should be doing it right here. I think what the problem is the resolution of our calculator is too low, and it can't get the lines close enough, so you can't really draw them. because it doesn't know which side to draw because they're so close together. So I'm going to zoom in over there and see what's happening. So zoom in at -3. Yeah, all right, now zoom in. Right there. I'm going to zoom in one more time. See, I'm starting to get a blue line there, and it's going down here. We can see that it's kind of splits apart. I bet if I zoom in one more time, we'll see something more along the lines of what we think. Yeah, now it's starting to split up. You can see it. The resolution was just too low. We knew it should be there because we had a factor that gave us that answer. It comes down here to -3, and it bounces off the x-axis. Anytime the multiplicity is even, that's how it's going to happen. So recognizing even and odd multiplicities by looking at the graph is important because it's going to help us when we start taking a polynomial that's not in factored form and trying to get those zeros, which is much more difficult than if it's already in factored form. Okay? But the graphic can help us a lot. Okay? So seeing that happen is nice. This one was in factored form. That's how we knew that one should be there. But we see it bouncing off the x-axis or going down and touching the x-axis. It could come up from the bottom and touch the x-axis and go back down. Either of those are indicating an even multiplicity. Even multiplicities bounce off the x-axis. Odd multiplicities, whether that be 1, 3, 5, 7, 11, 183 multiplicity, doesn't matter. It's going to cross the x-axis if it's an odd multiplicity. It's going to bounce off if it's an even multiplicity. Okay, so that's important to remember as we start moving forward after this section. Okay, all right. Next thing, this first section is pretty heavy in lots of things that you've got to just be able to recognize. Turning points. Polynomials have turning points. We've seen the graphs of them. They got those curves and all that going on there. In algebra, there's not really a great way to find those turning points. We need a little bit of calculus to help us with that. But we can tell how many there could be with a quick, easy formula. Turning points. Polynomials of degree n have at most n minus 1 turning points. How many turning points could f of x equals x cubed plus 3x squared minus 5x plus 4 have? What's the degree of f of x? The degree is 3. Turning points would be n minus 1, which is 3 minus 1. 2 turning points. It might only have 1 turning point, but it could have 2. Okay? That's what we're finding. That's always a question on the final exam. I've seen it almost every year that I've taught this, and I'd say every year, but every semester I've taught this, they've asked that simple question: how many turning points could this polynomial have? In the degree minus 1 tells you how many turning points it could have. Doesn't tell you where they're at or anything like that, but it just tells you how many it could have on the turning points. Okay? All right. Let's build polynomials before we start breaking them apart. Okay? So let's build a polynomial in standard form. So we're going to build a polynomial that has zeros 1, -2, and 3, and it has a degree of 3. We've got 3 zeros. It has a degree of 3, so that means we don't have to worry about multiplicities on this one. If we do have to worry about multiplicities in this type of problem, they're going to tell us, and we'll do an example of that in just a second. Okay? So what we've got to do is start with building the polynomial using the factors that go with those zeros. If 1 is a 0, what factor did that come from? The simplest way to write that. X minus 1. Good job. If I set that equal to 0 and solved it, I get positive 1. That's why that works. -2 would be what as a factor? X plus 2. And then 3 would be X minus 3. That's simple. Super easy to do like that. Okay? Now, that's intercept form or factored form. Doesn't really matter. It's not standard form. We know standard form should have a sub 3 x raised to the third power, and then something squared, something plain, and then a constant on the end. So we've got to multiply this out. Which 2 you pick to put together first doesn't matter. Just pick 2 of them and multiply them together, and then distribute the third. So I'm going to multiply. I'm going to do these 2 together first. It does not matter which 2 you pick to go together first. It's not going to change your answer at the end. So I'm going to multiply x plus 2 times x minus 3. So that'd be x times x is x squared minus 3x, and then distribute the 2. So that'd be plus 2x minus 6. The x minus 1 is still there. Haven't done anything with it yet. I'm going to go ahead and simplify that quadratic x squared minus x minus 6. You don't have to do that, but it does sure make things a little easier on the next step. If you don't simplify, it can make things harder. Just longer, not just harder. Okay. Then I distribute the x minus 1 to all of that and multiply that out. So x times x squared is x cubed minus x squared minus 6x. And I'll show you kind of my trick to helping me do this more efficiently. And that's just using distributive property, but then I stack it. Like when I distribute the x times x squared, that goes here. Then I'm going to distribute the -1. -1 times x squared, I'm going to put that under here. And then, that way I stack up my like terms. It just makes it maybe a little bit less jumble. That'd be -x squared, positive x, positive 6. And then I add them up. X cubed minus 2x squared minus 5x plus 6. That's my polynomial. Now, here's how I can decide if that's correct. If we were to graph this, where should it cross the x-axis? At 1, -2, and 3. So if I graph that, x raised to the third minus 2x squared minus 5x plus 6. And I'm going to have to hit zoom 6 to get it back to a normal window. Anytime you zoom in or zoom out with your calculator, zoom 6 will get you back to the normal place. Look where it crosses the x-axis. There's 3, there's 1, there's -2. It's the right places. That's a good checking method for multiplying out a polynomial. If you know where it's supposed to cross the x-axis, you multiply it out, graph the multiplied out form, and see if it crosses those right places. If it does, it's very unlikely that you made the right mistakes to make a polynomial cross at the right places, but be a different polynomial. It's very unlikely that that happens. Okay. All right, so let's look at one that the multiplicities is involved with. And then we'll move on to the breakdown sections. Here are our zeros. -3 with a multiplicity of 2 and 5. as degree, we'll just go to degree 3. So the key to doing this is just start with the factors. If -3 is a 0, what's the factor that goes with that? X plus 3. How many of those should there be? 2, because it has a multiplicity of 2. And absolutely, that's how I would start out, is putting x plus 3 squared. And then what's the factor that goes with the 5? X minus 5. Good. Now, you can maybe skip that step, because what do we know about x plus 3 squared? That it's really x plus 3 times itself, right? It means that factor occurs twice. And then we're back to where we were with the last example where multiplying always jumped out. Anytime I have a factor that has a higher multiplicity, I usually start with those two together first. You don't have to do that. You could just start with these two and go from there. Doesn't matter. But I usually generally start with those first. My way of doing things, I guess. So I'm going to multiply these two together, and that'll give me x squared plus 6x plus 9. Part of that is because I know when you square a binomial, how to get all the pieces. Shortcut there. Square the first piece, square the second piece, then multiply them together and double it. And then distribute the x minus 5 to that. So I'm going to distribute x first, so that's x cubed, 6x squared, 9x, and then the 5 be negative 5x squared, negative 30x, and negative 45. Final answer would be x cubed plus x squared minus 21x minus 45. What do we know the graph of this thing should do at -3? What should it do to the x-axis? Cross it or bounce off of it? Why? Because it's got an even multiplicity. So if we graph this, we should be seeing we got x to the third plus x squared minus 21x minus 45. If we graph that, we should see it bounce off at -3. Go here to -3. That's what it's doing. It's coming up from the bottom, but it's bouncing off of the -3. That means we did something right. And it's crossing at 5. 1, 2, 3, 4, 5. That's crossing. It's an odd multiplicity on the 5. You can see that happening. Being able to tie that together can be very helpful when you go when we're going to the next steps here. All right. There's section 1. Let's get into sections 2 and 3. A lot of stuff tonight. 5.2. Real zeros of a polynomial. All right. First thing we need to talk about is long division. And then we'll talk about synthetic division as well. Long division, you're not going to use a ton in this particular section, but we will use it in next week's lessons. Okay, so long division, synthetic division go together, but in today's particular lesson, you're not going to use long division much, but I want to show it to you and then show you how synthetic division gets you the exact same result out of this. So we're going to divide x cubed plus 4x squared minus 5 divided by x minus 3. Okay, and we're going to use long division. I remember doing long division back in elementary school. May have been quite a long time since you've done that sort of symbol not just done division or reduced the fraction or something like that. So now, when you go to do either long division or synthetic division, you've got to look at the degree of the polynomials that you're dividing into and by, and make sure that you have a representative for each power, starting with the highest one. So the degree of the first one is 3. So that means I need to have a representative for x cubed, x squared, plain x, and then a constant. So I got to have 4 terms in here, because a third degree polynomial has 4 terms. If there is one missing, you put a 0, whatever's missing in its place. Okay, so for this one, on the inside, I'm going to have x cubed plus 4x squared plus 0x, and then a minus 5. Okay, I put the 0x in there because it's missing from what you're dividing into, also known as the dividend. Okay, the divisor has a degree of 1. That means I need an x and then a number. So degree 1, you're okay there. If it were x squared, you'd need an x squared, a plain x, and a number. So you got to look for that in the divisor and the dividend, what you're dividing into. Make sure there's a representative. It's going to help you a ton when you're lining things up and getting things done. Okay? So when you're doing long division, you're going to look at the term in the front of your divisor, what you're dividing by. We've got an x there. We want to know what times this x would get me x cubed. What times x gives me x cubed? X squared. Good. So I'm going to put that above the x squared. So it's kind of like, I like to line it up in columns. Some folks don't line them up, and that's okay. It works, but I'm a little bit organizational. I don't like to say OCD. I like to think organizationally minded when it comes to how you do things. So lining up, it really just seems to make sense to do it that way. All right, so now we know that x times x squared will give us x cubed. So what we're going to do is we're going to take whatever we put up here and multiply it times everything that's out here. So x squared times x gives me x cubed. So I'll put x cubed right there underneath. X squared times negative 3 would give me negative 3 x squared. Then I'm going to put that in parentheses and subtract. This is just like if you were going to divide numbers back old school elementary school style. Okay. Next thing I do is I subtract. What happens to the x cubed? What's x cubed minus x cubed? They go away. It's 0, right? It cancels out. That's what we want to happen. But then I do 4x squared minus negative 3x squared. Okay. So the x cubes cancel out. 4x squared minus negative 3. What's 4 minus negative 3? 7x squared, right? Right. Now, I'm going to bring down the next term. I remember in elementary school, you always brought the next number down. So I'm going to bring down the 0x. Even though it's 0x, I'm still going to bring it down. The reason I'm going to bring down just 1, how many terms am I dividing by? 2. I need 2 of them right here. Right? Okay. So now I look at the front again. What times this x would give me 7x squared? A 7x. So I'm going to put a 7x up there. It's a positive 7x, so I'll put plus 7x up there. Okay. Then distribute. 7x times x, 7x squared. 7x times negative 3, negative 21x. Parentheses, subtract. You're going to hate me when we do synthetic because it's much easier. It's short. If you haven't ever done synthetic, it's easier. All right, now subtract these. 7x squared minus 7x squared. We'll cut each other out. Okay? 0 minus negative 21. Be positive 21x. Okay? So these cancel out. I'm going to bring down the minus 5. Now, What times x get me 21x? 21. Positive 21. So that gives us 21x minus 63. Parentheses, subtract. 21x's cancel out. We have negative 5 minus negative 63. So that'd be negative 5 plus 63, which would be 58. Is there anything times x that will get me 58? No. This is smaller degree than what I'm dividing by, so I know I'm done. That right there is my remainder. Okay? In polynomial division, the way you write that answer is you have your quotient, x squared plus 7x plus 21. That's your quotient. Remember, the answer to a division problem is quotient. Plus the remainder, 58, over what you divided by. This is our quotient. This is our remainder. What the remainder is very important. Because when it's 0, that means something special is happening. Okay? Doesn't mean it has to be 0. It just means when it is 0, special things are happening. Okay? This is our quotient. This is our remainder. We always write it with a remainder over what we divided by. Okay? Let's do it with synthetic division. And I'll show you how much faster and easier it is. Okay? Synthetic division. With synthetic division, you always you start with the same thing, f of x, or let's say we're dividing x to the third plus 4x squared minus 5 divided by x minus 3, right? That's all the signs the same. Yeah. All right. With synthetic division, you take your divisor, what you're dividing by, and you set it equal to 0 first. Okay? Synthetic division can only be used when you're dividing by a linear polynomial. Okay? That's important. Okay? Synthetic division can only be used when you're dividing by linear polynomials. Okay? If you're dividing by a quadratic or anything bigger, then you have to use long division. So linear polynomials are the only thing we can use synthetic division with. That's not a bad thing. That's a good thing. Most of the things we're going to deal with, we can break down into linear pieces anyway. Okay? Now, what we want to do is take that linear polynomial that we're dividing by, set it equal to 0, and solve it. So add 3, x equals 3. This number, I call that my shelf number. That's my shelf number. So if I say, what's the shelf number? You know where that came from. It came from setting the divisor equal to 0 and solving. That's the shelf number. Now, let's set up the synthetic division. This is how you set up synthetic division. Make yourself a little, like a laying down L. Backwards. L. Then I put a shelf on the outside here. Kind of looks like we're about to play hangman or something. Okay? That number, my shelf number, goes on the outside there. This is where the 3 goes, right here. On the top row of the inside are going to be the coefficients of the polynomial I'm dividing into. And remember, with long division and synthetic division, I have to take a representative from the highest power down. So the degree of that polynomial is 3, so I know I've got to have a cube, a squared, a plain x, and then a number. Okay? So I've got a 1, because that's the coefficient of x cubed. So it's a 1, so I'm going to put a 1 right there. I'm I'm going to put a 4 for x squared. I don't have a plain x, so I'm going to put a 0 in its place, and then a minus 5. Make sure you take the signs with you. Now, notice that there are no letters in there. That makes things infinitely easier because you don't have to deal with multiplying x times x squared and messing up the exponent and all that fun stuff. They can have you. All you're dealing with are numbers. Okay? So the first step every time in synthetic division is drop the first number down. Put it right there. That 1 drops down. Then we multiply. 1 times 3 is 3. Drop it down, multiply. 1 times 3 is 3. In synthetic division, we always add. Long division, subtract. Synthetic division, always add. Okay? What's 4 plus 3? 7. Then we multiply. 7 times 3. 21. What's 0 plus 21? 21. 21 times 3? 63. Negative 5 plus 63. Remember, we're adding. 58. That number that's on the end down here, that's your remainder. Is that the same remainder we got for example A? Absolutely. Was this easier? Absolutely. Okay, here's what we got out of that. We took a cubic or a polynomial here, and we divided by a linear one, so it reduces the power by 1. This is now a quadratic. 1x squared plus 7x plus 21. Is that the quotient we found for example A? That's exactly what that is. X squared plus 7x plus 21 plus remainder 58 over x minus 3. Synthetic division is going to be your tool. You're going to use that a lot. Okay, so make sure you remember. Drop the first term down, multiply and add, multiply and add, multiply and add, always. Synthetic division, multiply and add. That's what we got to do. Okay. There's this thing called a factor theorem. It says that x minus some number c is a factor of a polynomial if f of c is equal to 0. All that's magical math terms for meaning if I divide by x minus c and get a remainder of 0, then x minus that number was a factor of my polynomial. Okay? What we're going to do here is we're going to test to see if something is a factor of a polynomial. Okay? Is x minus 1 a factor of f of x equals 2x. Why did I put parentheses there? 2x cubed minus x squared plus 2x minus 3. Okay. Is x minus 1 a factor of that? So here's what we're going to do. We're going to divide f of x by x minus 1. That's what we're doing. Is x minus 1 linear? Yeah, that means we are allowed to use what? Synthetic division. That's the one we want to use. Long division, it's long division. Nobody likes it. Okay, so we don't use it. So we can use synthetic. So first thing we got to find is what? Shelf number. So x minus 1 equals 0. It'd be positive 1, right? So a positive 1 goes on my shelf. And then I put in coefficients. I have x cubed, x squared, x constant. I've got all the pieces for this one. I don't have to put any zeros in there. So 2, -1, 2, -3. Make sure that polynomial is in descending order so that you don't mess up your synthetic division. Because once you take the x's out of it, hard to look back and see. Just make sure it's in descending order before you start. Okay? What's the first step for synthetic division? Drop the first term down. So 2 comes down, and we multiply. 2 times 1, 2. And then what? Add. -1 plus 2, 1. Then what? Multiply again. 1 times 1, 1. Add. 2 plus 1, 3. Multiply. 3. What's -3 plus 3? 0. That right there, the remainder being 0, tells us x minus 1 is a factor. Here's what it does for us. It factors that polynomial that was a cubic polynomial into this linear piece. And then what is this part? What does this turn into? This 2, the 1, and the 3. It's actually the quotient, right? What's the quotient there? 2x to the second plus 1x plus 3. It helps us factor that larger polynomial. Right? If we wanted to find the zeros for that, well, we already know that 1 is a 0 of this. That's quadratic. We got a lot of tools for solving quadratics. We got quadratic formula, we got factoring, we got all those things that we can do with that. So using this synthetic division to decide if something is a factor is going to help us solve polynomials as we move through the next 30 minutes. Okay, so let's look at an actual polynomial and try to do that. Okay. Find all possible rational zeros and factor. Here's our function, f of x equals 2x cubed plus 11x squared minus 7x minus 6. Okay? All right. So that first part we haven't talked about yet. The factoring part we've talked about a little bit. We're going to do all of that. So if we're talking about factoring and the possible rational zeros, there's this thing called a rational zeros theorem. The rational zeros theorem says that you can look at the coefficients, the leading coefficient and the constant term, and find all of the rational zeros that are possible for a polynomial. It doesn't mean that all of them work. It just means the ones that it could be. If there are rational zeros, it's going to be in this list. This list is P over Q. P is the constant. Q is the leading coefficient. Okay? To find the list of possible rational zeros, we need all the factors of P divided by all the factors of Q. Okay? Factors mean numbers that divide into that number evenly. Okay? So factors of P in our problem here is 6. So what are the factors of 6? What are things that multiply to give me 6? 2 and 3, 1 and 6, right? What are the factors of 2? 1 and 2. That's the only ones. Okay? Now, here's how we make our list. We divide the top numbers by the first one on the bottom. So 1, 2, 3, 6 divided by 1. Okay, so we have our P over Q list, the possible rational zeros. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. That's the ones where we're dividing by 1. Then we take the numbers on the top and we divide by the next factor that's in the bottom. So we're going to divide all those by 2. 1 divided by 2, that's 1/2. That's a rational number. So we have plus or minus 1/2. And then what's 2 divided by 2? 1. We've already got it listed. We don't have to write it again. 3 divided by 2. We don't have that listed. So 3 over 2. Plus or minus 3 over 2. And then 6 divided by 2. 3. We've already got 3 listed, so we don't have to write it again. So here is our list of possible rational zeros. Okay? If the zeros of this polynomial are rational, it will be one of these 12 numbers that it could be. What we've done is we've narrowed down the possibilities for where this thing crosses the x-axis from all the numbers in the world to these 12. Okay? Now, is the rational zeros theorem a necessity? No, but it sure does help us when we start seeing some that don't cross at nice places. If we graph this thing and it crosses at 1, 2, 3, or 6, or the negative of any of those, that's easy to see. But I dare say that we would have trouble if it crossed somewhere in between 1 and 2. Because it's hard to eyeball what's the difference in 1/2 and 4/7 if you're just looking at it and you don't have anything to go by. So knowing that it couldn't be 4/7, it has to be a 1/2, or it couldn't be 6.5 repeating. It's got to be 1.5 as the fraction. So we know that those have to be there because they're rational zeros. This is always, and when I mean always, I mean every stinking time on the final. Just do this. Find the rational zeros list. That's on the final every single year. Every time I've ever caught the math board, that's on the final. You got to be able to do that. Okay? So make sure you can do this. Now, how do we use that? That's the important part. How do we use that? We get that list. What good does it do us? Okay, here's what we need to do. We need to take that polynomial and we're going to graph it. I'm going to go to y equals, and I'm going to type in the original polynomial, 2x to the third plus 11x squared minus 7x minus 6. I'm going to hit graph. I'm going to look to see where that thing's crossing the x-axis. Okay? Looks like it's crossing at 3 places. That means I have 3 real zeros. Okay? Every how many times it crosses the x-axis or touches it, that's how many real zeros I've got. If I read it left to right, the first one I come in contact with is right there. It looks like -6. It's possibly 1. What would this one possibly be? -1/2. This one would possibly be 1. All of those are in that P over Q list that we made. Okay? So if it's crossing the x-axis at good spots, then it's going to be in that P over Q list. Here's the thing. It doesn't matter which one you start with. Pick one that you think is easy to start with. Of those 3 numbers, -6, -1/2, or +1, which one's the easiest mathematically? 1. So that's the one I'm going to start with for my synthetic division. Okay, so that's what I want to do here. So I want to take this polynomial and I want to do synthetic division with a 1. So I have 2, 11, -7, -6. Okay, so we graphed, pick a 0. Okay, that's the next step. Make your P over Q list, graph it, pick a 0. Pick a place where it crosses the x-axis. Use that 0 as the shelf number for your synthetic division. Run the 1 through with synthetic division. 2, 13, multiply That'd be 6. If you don't get 0 as the remainder, when you do that, something went wrong. You missed a sign somewhere, maybe you even miscopied the problem. That's what's happened. Or you graphed the wrong problem. Okay? Now, we now know what's the factor that goes with positive 1 as a 0. X minus 1. Remember back in section 1 when we built those polynomials, if we knew a 0 was a positive 1, then the factor that it goes with is the opposite sign is x minus 1. What's this turn into? 2x squared plus 13x plus 6. It's a quadratic. If I want to factor this polynomial, that means I need to try to factor that quadratic. Okay? We did this back in chapter 4. We factored some quadratics. I use that X method thing where you say 2 times 6 to get that number up top is 12. We need numbers that multiply to be 12 and add to be the number in the middle. What multiplies to be 12 and adds to be 13? 12 and 1 does that. So that means I go 2x squared plus 12x plus 1x plus 6. And then I group. 2x in common, that gives you x plus 6. Those don't have anything except for 1 in common, giving you x plus 6. So that factors as 2x plus 1, x plus 6. What's the factor we already knew about? X minus 1. There we have the factored form of that polynomial. If I set each factor equal to 0, I'm going to find the zeros. We already know what they are because we saw the graph crossing the x-axis there, right? We saw it crossing at 1. This one, what's that one going to equal if you set it equal to 0? Negative 1/2. This one's going to equal you the negative 6. We saw those on the graph. This is the map that happens to be that factor. So here we have the factor form. We get the zeros. All that is included out of that. Let's get this one. Find the zeros and factor f of x equals x to the 5th minus x to the 4th minus 4x cubed plus 8x squared minus 32x plus 48. This one has a little more lengthy P over Q list. We're going to make that first, and then we'll graph it and hopefully find a few that work. Okay. So factors of P. P again is your constant always. Constant is always going to be the number up top. The factors of 48. So factors of 48. This one's a little tougher to get. I'm just going to put 1 plus or minus in the front and then list them instead of writing plus or minus over and over. Okay. The bottom part's easy. It's 1. The leading coefficient is 1, so that makes this list super easy. As far as I don't have to have I don't have any fractions. So the factors of 48. So 48 is a fairly large number when you start talking about factors of it. So I know 1 and 48. I'll start there, and then I also know 48 is even, so that's 2 and 24. Does 3 go into 48? Yeah, 16 times. 4 goes into 48. 12 times. 5 doesn't go into 48. 6 goes into 48 8 times. 7 doesn't go into it. 8 does go into it. We've already done that, so I've started repeating myself once I get there. So dividing all of those by 1, I know that these are just my P over Qs. 1, 2, plus or minus 1, 2, 3, all the way to 4. That list. That's my P over Q list. Okay? Now, from there, we then look at the graph of our polynomial. So we're going to graph this thing and look for which one of these is it crossing the x-axis at. We're going to use those to do our synthetic division. Okay? So the graph. Y equals, clear that one out, x to the 5th, x raised to the 5th, minus x raised to the 4th, whoops, x raised to the 5th, x raised to the 5th, minus x raised to the 4th, minus 4x raised to the 3rd, over plus 8x squared minus 32x plus 48. Check all your signs. Make sure you got them all right. Looks like I think I do this time. Hit graph. All right. Interesting things happening with this one. All right. Where is it crossing the x-axis? -3. Where is it touching the x-axis? 2. What does that mean about 2? The multiplicity is even. We don't know if that is 2 times or 4 times, but we know that 2 works at least twice. Okay? We know that 3 works once or 3 times. We know it can't work 5 times because we got somewhere else that's touching the x-axis. So it can't be all 5 of the zeros. Okay? So when you do your synthetic, pick one of those to start with. I'm going to pick the one that has the single multiplicity, the odd multiplicity first, and see what happens. I'm going to do synthetic with that -3 first. If you use the 2 first, it's okay, but you're going to have to use it twice anyway. Okay, so I'm going to set up my synthetic. Got the -3 on the shelf. 1, -1, -4, 8, -32, 48. So a little long on the synthetic here. And I'm going to kind of keep myself organized. You know me, I'm organizationally minded. I'm gonna write a little table. I'm gonna have the 0 over here and the factor that goes with it on the right. Because it looks like this is going to be kind of long-ish. Okay? So let's run that synthetic through with the -3. So I'll drop the 1 down, multiply. The -16. +16. And I got a 0 in the remainder. It's what I should get. Now, so that means I have a 0 of -3. What's the factor that goes with that? Good job, x plus 3. Okay. Now, here's what I want to do. I've broken this polynomial down. It started as an x to the 5th power. This would be an x to the what? 4. I'm going to use that smaller one to divide with my other zeros that I know about. The other zeros that I know about are 2. And I say are 2 because it happens twice. At least twice. It may go 4 times. I don't know. We don't know that yet. Okay? So I'm going to put a +2 on the shelf because that's where it's touching the x-axis at, +2. Then drop the 1 down and go from there. -2. 4, 8. What do you know? I got a 0 in the. So that means 2 is a 0. The factor that goes with 2 would be x minus 2. I know that 2 works at least one more time. So I'm going to do synthetic on this. We started with x to the 5th power. This became x to the 4th power. This is x cubed. So I'm going to do synthetic one more time on that. Okay. I'm going to put a 2 on the shelf again. Drop that down. 1, 2. There's a 0. And then 0. That's 4. There's positive 8. All right. It worked out again. So 2 is a 0 again. It has a factor of x minus 2 again. What degree is this? X squared. Once I've done synthetic enough to get this down to a quadratic, I usually stop doing synthetic because I know enough about quadratics. I know I've got quadratic formula. I know I can solve by square roots sometimes. I know that I can factor quadratics using an x thing. Okay? So that's usually where I stop. You don't have to stop there, but it's always a good idea because it's quicker than trying to, stumble around and find another 0 that works. 2 does not work again for this one. If I try to run a 2 through this with synthetic, let's say I thought, well, maybe 2 worked 4 times. If I ran a 2 through right here, and that's positive 4, that doesn't get me a 0 as the remainder. So that's how I know that 2 doesn't work again. Okay, so I'm back to here. This is x squared plus 4 as a quadratic. I'm going to set that equal to 0 and solve it. This one is best solved by using square roots because I can just move the 4 over and then take the square root of both sides. Right? What happens when you take the square root of a negative? Complex numbers. I. Square root of negative 4 would be 2i. Those are not real zeros, but they are zeros of the polynomial. Okay? Here's the factored form of our polynomial. We've got x plus 3. That was the first one we used. Remember from our factor up here? Then we had x minus 2. How many times did we use x minus 2? Twice. So it's got a squared on it. And then I'm going to use x squared plus 4 as my third factor because it doesn't have real zeros. It's got complex zeros. So I'm just going to leave it as that quadratic there. And you wouldn't know that unless you solved that quadratic to leave it that way. If this were a quadratic like x squared minus 9, you could factor it as x plus 3 and x minus 3 and it would work out a little further. But because this doesn't factor, we leave it that way. Okay? Always look at that quadratic and look at that. A good rule of thumb for polynomials. Take the degree of the original polynomial, subtract 2 from it. That tells you how many synthetic divisions you should do. So this one had a degree 5. 5 minus 2 is 3. How many synthetic divisions did we do? 3. That gets you down to a quadratic. If you had a 4th degree polynomial, 4 minus 2 is 2. That means you're going to need to do synthetic twice to get there. That's going to be your ticket there. Let's look at one more here that's got complex solutions involved so that you've seen that and go from there. So let's try this one. This is actually section 5.3. I blend them together because they're the same thing. There's nothing different in 5.3 as far as finding the zeros of the polynomial. So let's let's try this one. F of x, 3x to the fourth, 5x cubed, plus 25x squared, plus 45x minus 18. I don't know what number this is. F. So we get 1, 2, 3, 6, 9, and 18. Then we get 1/3, 2/3, 3 over 3 is 1, 6 over 3 is 2, 9 over 3 is 3, 18 over 3 is 6. Okay. There's our P over Q list. Factors of the constant over factors of the leading coefficient. That gives you your P over Q list. Possible rational zeros. What's the next step? Put the equation in the calculator and graph it. That's exactly right. So y equals 3x to the fourth plus 5x cubed, plus 25x squared plus 45x minus 18. And graph it. See where it's crossing the x-axis. Looks like it's crossing at -2. And what could that fraction be? Could be 1/3. Could be what else? Could be 1/3 or 2/3. It looks closer to 1/3 to me. Whoops, wrong picture. Looks closer to 1/3 to me. So I think that's the one we'll use when we get to that. So which one's easier, the fraction or the non-fraction to do synthetic with? The non-fraction. So I'm going to use the -2 first with my synthetic. On my synthetic, on the shelf, I'm putting -2. 3, 5, 25, 45, -18. Run that through. Drop down, multiply. It's -6, adds to be -1, +2, adds to be 27, be -54, -9, and that's +18, and that gets me my 0 in there. So I'll get a 0 of -2, a factor of x plus 2. Now for this one on the shelf, I'm not just going to have an integer. I've got a fraction because I know that that's where that should be crossing. I know that I should be using that because here's how you know that number is the right one. You can hit trace and then type in 1/3 and hit enter. Notice that it gets you the y value of 0. You know that's why 1/3 should work in synthetic division. Same thing with the -2. If I hit trace and type in -2 and hit enter, I get a y that's a 0. So that's how I know that that number works in synthetic. So maybe you want to do that before you actually do the synthetic to make sure that that number is right. Okay. So from there, I've got a 1/3 that I'm putting up there. Synthetic with a fraction is the exact same as synthetic with an integer. You just got to deal with multiplying times a fraction. I'm going to drop the 3 down. This one works out really nice because 3 times 1/3 is 1, and that's 0, and that's 0, and that's 27, and 1/3 of 27 is 9, and that's the remainder, 0. So we get 1/3. The factor that goes with that would be 3x minus 1. That's the factor that goes with that. Now, that leaves us 3x squared plus 27 equal to 0. Okay? I can solve that by square roots because it's quadratic, or I could use quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac divided by 2a. If I'm just looking for the zeros, then quadratic formula works great. This one's solving by square roots works great too on this one, but it's same answer either way. So that'd be 0 plus or minus 0 squared times 4 times 3 times 27 over, that's 2 times a, 6. So we end up with plus or minus the square root of negative, whatever 4 times 3 times 27 is. 4 times, whoops. 4 times 3 times 27. Big number. 324. All that divided by 6. So I would break down 324. I know I got it from 12 and 27. 4 and 3. 2 and 2. That's 9 and 3. That 1. Oh, this just works out to be a nice perfect square. A pair of 2s, a pair of 3s, and a pair of 3s. So that's 9, 18 I over 6 plus or minus 3i. So my zeros, my x-intercepts, are at negative 2, 1/3, and plus or minus 3i. All right, guys, we are out of time. I'm going to link you to